Thanks, everyone. So Stephen recruited me to chair a session, and I tried to chair the first session, but since he's seen Sharad's talk a few times, he predicted that there might be like lots of questions, and this would be like the more difficult session to chair. So here I am. So anyways, it's a very good talk.
Bad introduction. Not at all controversial. And I think Aaron, this will be the third time that Aaron has seen this talk in like the last month, so I apologize in advance.
Maybe Aaron can give it?
Probably. We've been following each other across the country. Okay, so I want to open up with a summary, and it's, as maybe Aaron alluded to, there are a couple controversial points here, so I want to put them up front, and please push back. The first is kind of in line with what we saw in the morning sessions, that I'm going to beat up a little bit on these group-based notions of fairness that are, I would say, somewhat popular still. And I'm going to argue that most of these mathematical measures of fairness, these group-based mathematical measures of fairness, are poor proxies for detecting discrimination. I'll try to be precise about what I mean by discrimination. And even worse, attempts to satisfy these formal notions of fairness can lead to perverse decisions, perverse outcomes that many people would call discriminatory. And so not only can you not measure the discrimination in many cases, acting on these measures can lead to discriminatory behavior. So I'm going to break this up into three parts. The first part, just give you a little bit of background on algorithmic decision making. I think most of this will be familiar to people, but just to set the stage. And I'll put everything in the context of criminal justice using the ProPublica, the standard ProPublica example, but to keep things concrete. But the arguments I'm going to be giving are much more general. Okay, so to make sure we're all on the same page in this pretrial setting, what happens in the US is after you've been arrested, usually within 24 to 48 hours after someone's been arrested, a judge has to make this high-stakes decision about whether or not to detain you or release you pending trial. There are competing interests here. On the one hand, there are these social interests and even the state's financial interest in that detention is expensive. Detention will disconnect people from their families, often to lead to loss of employment. And on the flip side, there's the state's interest in ensuring public safety and ensuring that people show up to trial when they're asked to. And so this is a hard decision. It's consequential, certainly. And the way that this is typically done, still in the US, is that judges use their experience. They use just knowledge of how people might behave to make these decisions informally, usually in pretty quick, like 2-minute interviews. And so there's this movement to shift to an algorithmic way of guiding these decisions, not making them exactly, but guiding the judicial decision by risk assessment.
I'm sorry.
Yes, please.
I thought that you said that there was a sort of individual interest versus a state's interest, but in fact, both of them are both.
Both are both, yes. Both are both. Yeah, and so there is they're both on the state side. When someone is detained, there's a financial cost, so that's quite expensive. That's one state, and also the employment.
Yes. And that causes costs in the state in the future.
Yes, so it is this complex. And really, I want to say there are these two, I would say in the extreme version of it, there are these two sides that one might consider, but in reality, it's much more intertwined. But that's often how it's presented, that the state might just say, let's have this kind of authoritarian government. If we don't want any crime right now, we're going to lock everybody up. On the flip side, if we understand the cost of detention, we might release everybody, and then there's this interplay here. So it's a difficult balance to get. Okay, so I'm going to make two key mathematical assumptions for the rest of the discussion. And the first one particularly is quite important. So I'm going to assume, so these are risk assessments, and so how these risk assessments work is you're trying to predict something like the likelihood, you're trying to estimate the likelihood that someone will commit a violent crime if released, something like that, or the likelihood that they won't show up to court if released. And I'm going to assume, so think of this as just like a regression or something, that's what's actually used in practice. You have the left-hand side, and you have this label y, and I'm going to assume it's a true label in two important senses. So the first is that there's no measurement error. So if I say that 1 might indicate that you committed a violent act, in reality, it's very hard to measure that, because if somebody committed an act, you only know it through proxy. For example, you know it if they've been arrested, or you know if they've been convicted, but usually you don't know whether or not they actually did it. So I'm going to assume for now that we actually know that they did. I'm coming back to this at the end, but I also want to flag, this is probably one of the hardest things about fair machine learning, or whatever you want to call the subfield, is that we don't actually have access to that label that we're trying to predict. And the second sense in which I mean this is a true label is that it's a counterfactual. I want to know what would have happened or what would happen in the situation that I've released them. And you don't know that because you're training on some data set. Some people release, some people are not. So again, it's very difficult to estimate this thing. So it's true in the sense that it's both the counterfactual and it's also perfectly measured. And so all of those are put into this label. So it's a very big assumption. And I'm going to argue that even under this assumption, all sorts of crazy things can happen. And when you have violations of this, it's not that somehow magically these definitions that people use fix everything. And so I'm just going to put this out at the beginning, and I'll come back to it. Now, the second one is very much related to the two talks we saw this morning, in that I'm going to assume we know the true risk. And here I'm going to be very specific about what the true risk is. It means this conditional probability. So probability that y equals 1, conditional on x equals little x. So this is a feature vector. And exogenously, we're given this big X. So this might be, for example, your criminal history, your age, something like this. It just like enumerates various attributes about you. And now this is a particular instantiation of it. And if we have lots of data, everything is discrete. This is just, you could just say this is the frequent, you can estimate this by frequentist notion of conditional probability. In general, you're going to have to do some smoothing, and this is where all these multi-calibration notions come in. And so I'm going to sweep most of that under the rug, and again, assume that we just have access to this true risk. And notice there's no like idea of P star here. So we heard kind of allusions to the like, kind of philosophically difficult notion of probability. And here, again, if you think about discrete, lots of data, if you're really in this frequentist world, once I give you the X, then there's not a lot of philosophical issue there. I'm not saying this is somebody's inherent probability of recidivism. That's not a thing that I think is personally well defined. But I can say conditional on these attributes, that's just a subgroup. How many people in that group, or what proportion of people in that group recidivate? And that's exactly the meaning of this thing. So I'm trying to sidestep the philosophical issues of P star while also being precise. And then the choice of X matters, as we'll see. Yes?
So you're saying you want this to hold for every little x or just for some little x's?
No, I'm going to say we have this for all x's,
Okay,
all little x's.
So that seems particularly problematic when combined with one when we're thinking about x including certain criminal histories.
Yep.
Right? Because certain criminal histories, we would imagine we have virtually no data about why. Right? Like if you have a sufficiently violent criminal history, we might never let you out. Right? So like, I'm just pushing on number 2 a little bit because it seems as though if you want it for all x, it's going to be virtually impossible to satisfy.
I would say in practice, I would say it's not actually that bad, at least in the criminal justice setting, because typically people are using something like 10 features, and
there's no combination for which we almost never let people out. That's the thing.
Yeah, so you're right that in the extreme, and so this is where the generalization is coming from, and this is so some people just by statute, whether or not this is good or bad, we just don't release. So if you're an alleged murderer, typically you're not going to be released. And it might in fact be the case that they actually have low probability of failure to appear, a flight risk, but it's very hard to estimate that. And in part, this is also coming in on assumption 1. So again, the structure of this is not that I actually believe these statements. And I'm going to very much kind of beat up on this first statement that I think this is a very big assumption. But the structure of the argument I'm going to give is, even if we're in this nice world, all sorts of bad things can happen. Okay. So now, what is the general pipeline? That we have features, so think of this as criminal history, age, et cetera. We make some prediction, and then we're going to make from this prediction, we're going to make some decision. So this is like a probability. Then this is a binary decision, so detain, yes or no. And for simplicity, I'm thinking everything's binary. And the way I drew this is decision can depend both on the prediction and also the features. So in a sense, this is redundant. I don't actually need this formally. But the reason I'm putting this here is to highlight the importance of the prediction aspect when coming to our ultimate decision. Okay. So now let's just look at this first box. So here on the prediction, given the assumption, the second assumption, this is just given to us. So once I tell you the capital X, a set of features that I'm considering, this is just given to us. We have this by assumption. Okay? And now let's think about what the effect of the feature set is on that. Yes, please.
Should we think of prediction as the machine learning algorithm and decision as being a human decider?
Yeah, in both of these, they have a human and machine aspect to it. And here, you have to you have to decide on your feature set, and that's what's going to be in the X here. But once I set X, this is just given to us. Either we fit this model, or we just have some oracle that's going to tell us this. The decision, again, this can be informed by statistics, it can be informed by a model, but you're right that often this is the policy aspect of it. Okay, so now what does this thing look like? What does this risk look like? So I can think about this. So if I fix my x, what is this object here? It's a distribution of risk across my population. So in everyone in this room, I can say you have a 5% risk, you have a 3% risk, you have an 8% risk, you have a 2% risk. That's a risk. It's deterministic. I fit my model. It's a deterministic risk for everybody in the room. And so where is the distribution coming from? This is a density. Where is this coming from? This is from the distribution of my covariates in the population. So I might have a lot of people that have a combination of covariates that suggests that they're low risk. And then I might have a smaller fraction of people that have a combination of covariates that suggests that they're higher risk. Okay, so this is a distribution of risk. It's a deterministic distribution of risk across the population, where the distribution is coming from the fact that we have a distribution of covariates. So is that object clear? And so now, so this is really kind of the whole point. Like once we understand this object, everything kind of falls out very naturally. So I just want to pause for a minute to make sure we understand what this thing is. So what are a couple properties of this? So the mean of this, no matter what my x is, the mean is going to be the same. So the variance, the shape of this distribution can change as a function of that x, but the mean is going to be fixed. What is the mean? The mean is just the overall recidivism in the population. Right? That's just set. Right? Formally, you can see this because you're just taking the double expectation if you want, but it's also, I would say, intuitively clear. And what is a shape going to look like? Well, if I don't have a very informative feature set, this is going to be tight, low variance around the mean. If I have a super informative feature set, this is going to be high variance, and it's going to be more or less bimodal around 0 and 1. So it's going to look like this if I have a super informative feature set, and it's going to look like this if I have a low variance or a not informative feature set tight around the mean. Okay? And so the mean is fixed. The variance, the shape of the distribution, can change as a function of x. Okay, so now we understand a little bit about where the prediction is coming from and the properties of the prediction. And so how do we make the decision? There are many ways to make the decision. And I would say in practice, one common way is to threshold the risk. So you estimate someone's risk of recidivism, and now you're going to threshold it and say everyone who is quote unquote high risk or above a certain point, you might take one action. For example, you might detain these people and you might release these people. And where is this coming from? I mean, there are a couple ways to kind of justify this, but one way to think about it is that there, and first I want to make clear, this isn't the universal, this is common, and I've actually never seen anything that like deviates too much from this in practice, but it's not the only way that one could make these types of decisions. But I would say it's a reasonable way to start making these types of decisions, and it's encoding the fact that at this threshold, let's say this threshold is a 50%, what does that really mean? That means at the threshold, I'm willing to, oops.
It's a good time to update Flash.
Here.
Get the multitask.
It used to be that only Windows machines would do this. We've reached a new height for.
Pay for it. Okay. So at the threshold, what does this mean? If the threshold is 50%, it means that I'm willing to release 2 people and expect 1 crime. That's what that encodes. And so if I'm really willing to detain a lot of people, I might set the threshold way down here and say, well, I really care about crime, not detention. Again, this is immediate crime going to this point in the short term. And if I really say, no, I think that unless someone is super likely to go commit a crime, the costs of detention are so high that I'm going to put that threshold up here. So wherever I decide to put that threshold, that's a difficult policy choice, but it's encoding this fact that I have this certain trade-off between detention and crime, and that where I set that threshold depends on what that trade-off is. Yes?
I should think about just crime, not crime, and whether or not they return to trial.
I mean, you can think of this. You're right. In practice, people often do both, and then I'm going to have to combine these things and put some weight according to this. And now I'm going to normalize into units of crime. For example, I'll say 10 misses of trial are the same thing as 1 violent assault. But then I'll have to put it.
You can only use flight risk
Exactly. So in New York, for example, you can all use flight risk. So I'm being quite simple here to gloss over the details. Yeah. Yeah, and I think there actually is this like sort of moral argument for only considering flight risk over crime, although in practice, almost every jurisdiction looks at crime rather than flight risk.
So I'm going to do language police because twice you've talked about individuals having risks rather than what you expect when you release two individuals with this rating.
Yes.
But you've told me that you really only care about the second one, that you're assuming you don't have a notion of the first one.
So I'm assuming, so this is, I would say, using kind of standard statistical terminology, this would be the an individual's risk. So if I fit a regression, with
X is a feature vector.
Exactly.
I know,
And
but
there
I
are many
thought that
people
part
with
of
the
what
same
was
feature
going on
vector.
here was that you were assuming that there were many people that mapped to the same feature vector.
Yep.
So,
So you know a feature vector's risk, you don't know a
Yes.
person's
Yeah.
risk.
but I guess the reason I'm pushing back on this is that the notion of a true individual risk is not
no,
well
I
defined.
agree.
And
It's
so-
not even clear that it's defined or that it
Yes,
exists.
exactly.
People don't
And so
know
I would say
that.
typically if you were to like for example, we talk about, the probability of an election outcome, not the probability of an election with a certain structural feature. I mean, this is sort of standard terminology. And here I understand there's like a little bit of slippage in that we might really want to disentangle the individual from the features that are giving us that estimate, but
So when you released those two people,
Yes.
because you took the threshold to be a half, and you released two people, then you're assuming, you're predicting that one of them will, but you're not making any predictions that an individual one has a specific probability of a half, or are you?
Formally, we're not assuming any of that. This is really when I say individual risk, I'm literally saying the thing that came out of this. It's like you fit your regression, and now you have a feature vector, and now for every individual, really for every feature vector. But in practice, even if we have, the way that we generally go from the way we typically make predictions about individuals is we assume some regularization. And so you fit your logistic regression, we're assuming the world is smooth. And so even if we don't see anybody with the exact same feature vector, which is true in general, then we're still making individual estimates of risk. And so what's going into that, we're kind of interpolating between the frequentist, the world is divided into all these people with distinct kind of probabilities that are easily estimable, and then some smoothness that lets us interpolate in certain ways. So but all I'm really saying is this thing I'm calling an individual probability. If you want to say, if every time I say individual probability, you want to convert this to probability of an individual with that feature vector, that's totally fine. That doesn't change the discussion.
The randomness in that probability is over a randomly selected person with that feature vector.
Yes.
Yeah.
It's a question.
And that's why it depends. That's why it matters a lot what this big X is. Right. So if big X is
It's a question.
Right.
So when you say that it's reasonable when you have lots of data, do you assume that it's reasonable to find this risk given the features? Or are you saying that it's reasonable to assume that an individual who has this feature has close enough risk to this risk predicted by?
no. So the first. So the second is much harder. The first is saying that if I give you the little x, if I give you the big X, if I have a lot of data, you imagine, this isn't quite right, but I can imagine the world is into these discrete buckets. And so now I can just estimate pretty accurately what's happening in each of these discrete buckets. The second is a much stronger statement, and I actually do believe it in some cases. Like in baseball, we have kind of reason to believe that there's not some secret feature that's missing that's really going to let us, dramatically estimate outcomes much better than we have previously.
Good face, right? Wasn't that really important at some point in evaluating the probability someone was going to hit a baseball?
Totally.
Yeah.
I'm going to suggest
A
as the
good
moderator
face.
that we
Yes.
move on.
Like
Okay,
people
yeah.
differently.
So informally, you try. How do you get these things? You just try a bunch of stuff, and maybe you see some diminishing returns to information, and you feel like, okay, well, I haven't come across that secret sauce yet, so maybe I'm converging to some true probability. Although, again, referencing the first set of talks this morning, it's very difficult to know what that means, a true probability. Okay, so we've kind of in contrast to the single threshold, we have this double threshold way that we can think about things. We say we might do, if we have two groups, any two groups will have two different risk distributions. That's not something inherent about the group. It's just saying the covariate distribution is different in different groups, and so we'd expect different distributions of risk. And we might have different thresholds for different groups. Now, a lot of people would think that this is not fair, and I kind of hate using that word, but I'm going to use it here. And where is that intuition coming from? Well, there are a couple ways. I mean, first, there's this badge inferiority that might be saying, well, why am I subjecting different groups to different standards? Another kind of a econometric way of thinking about this is there's a loss of efficiency in that I'm detaining these relatively low-risk members of the blue group, and I could, if I switch to a single threshold, then I wouldn't have that issue, and I could detain fewer people for the same amount of crime prevented in expectation. So that's one kind of econometric way of thinking about why there's some value to having a single threshold. And this also goes under the name of no taste-based discrimination. So it's efficient in this very particular sense of if I care about immediate detention and immediate crime, then I'm optimizing that by using a single threshold. Okay. So again, I don't want to suggest that this is the only thing that one can do. But I do want to point out that this is a pretty reasonable thing that, first of all, that is done in practice, and I would say is something that's kind of has these legal and ethical ways of thinking about it that also I would say feels reasonable. And what the rest of the talk is going to be is looking at how different definitions treat this example. And so we're going to think of this as a litmus test of sorts, where when different definitions fail to capture this, or automatically would say this is an unfair situation, then that is something that I view as problematic.
Okay. Sorry, one quick question.
Yes.
Okay, so we've been talking about X as sort of fixed, right? Presumably our selection of X directly affects how differently this single threshold can
I'll talk about that in a minute.
Okay.
Yeah. Okay. So these three kind of ways of thinking about, or large classes of thinking about fairness, are not a complete taxonomy, but I think these are common ways of thinking about it. Calibration. Here I don't mean multi-calibration, I just mean ordinary calibration, so I'll get back to this in a minute. Classification parity. This is things like false positive rate, and then anti-classification, the not using protected group characteristics like race and gender. So I'll go through each of these slowly and see what's going on. Okay, so now kind of highlighted results. Calibration typically does not preclude taste-based discrimination. Classification parity almost always leads to taste-based discrimination, and anti-classification can lead to taste-based discrimination. So I'll walk through each of these in turn. So first, what does calibration mean? Calibration, so this is real data. This is from the ProPublica Broward County data. This is our analysis, but they show something similar. Here's a risk score, so 1 to 10. It's scaled here in deciles of risk nationally, but this maps to probabilities. And now I can say for any kind of risk score, what is the empirical probability of reoffending for different groups? And what we see here is that it's similar, and what I'm kind of slipping under the rug here is we never actually know the empirical probability because we don't have that true label Y, but we have a proxy for it, and so that's what's being plotted here. But it seems that if I tell you that someone has a risk score of 7, then their actual recidivism rate is comparable across different groups of defendants. Here, I'm showing white and black defendants. Okay, so that's what calibration is. So now, how do I have a calibrated score and still discriminate? So this is very much in line with these examples that we saw this morning, but I just want to play this out in this case. It's a slightly different example. Let's say that this is my rule. These are the true probabilities. I'm just going to say that I have a rich set of X's, and so I'm going to estimate these things, that this is what I believe that someone's probability is conditional on this rich set of X's are. And I know that you are going to make some decision and detain everyone above greater or equal to 0.5. Okay? Now I, again, am the algorithm designer. I want to discriminate, or I want to cause you to make different decisions. What am I going to do? And I like this blue group, and I want to make sure that no one in this blue group is detained. So what am I going to do? I'm going to do something very simple. I'm just going to take these people, these people that I believe are high risk, and these people that I believe are low risk. I'm going to average them together, and I'm going to say they're all medium risk. So this is very much in line with the example that Michael gave earlier of taking this 50% group and splitting it up into the 0% and the 1% group. But here I'm just doing it reverse. I'm taking the people that I think are high risk, people I think are low risk, and then making them all look medium risk. And the point is that all of them are now to the left of this threshold, so nobody is detained. And the stores are still calibrated, and so conditional on risk score, the actual empirical probability of recidivating is what you would expect. And so you can't tell from the outside that something funny has gone on unless you have access to more information, unless you actually can discriminate or distinguish between these medium risk people over here and these medium risk people over here, if you know that somehow they look different. And so you have to have access to some side information to do that. So this is like not really going to happen in practice, this type of strategic manipulation, but I think it could happen. I mean, this is like a particularly crude way of doing it, but I do think there are versions of this that can and have happened in practice. So you can think of this as a version of redlining. And so what was happening in redlining is that a bank did not want to extend credit to certain individuals. So how could they, to black individuals in particular. So how do they do this? They said, well, the only feature we're going to consider, one of the main features we're going to consider is where you live. So that's predictive of risk. So it's not like a crazy thing to consider where you live. But the problem is that there are a lot of other features the bank could have used. It could have used individual credit histories and said that even if you live in a high-risk neighborhood, a high credit risk neighborhood, which in reality is where a lot of black applicants were living, then you're going to be denied credit even if you are relatively creditworthy. And so this is a version of exactly that. I'm going to go to my high-risk neighborhood, and even though I can separate that high-risk neighborhood into people who are low risk and high risk, I'm not going to do that extra step, and I'm going to say everyone there is relatively high risk, and now I have a reason, based on calibrated scores, to deny credit to all those individuals. Okay, and so this is one argument for using all of the information that you have available when estimating these risk scores. So this goes to Jamie's comment of the risk, the X's you use matter, and if you don't use all the available information, then that can lead to these types of problems. But it's still trickier because the information that's available is not just like a well-defined thing. There's cost typically to getting information. And so you have to make this trade-off at some point of saying, do I want to spend the money to get better information or not? And that can obviously have pretty serious consequences for your risk estimates down the road. But I at least want to put that out there. And so at least if you have information available to you that's like zero cost, just sitting in your database, and you don't use it, that seems problematic.
Just in practice, calibration is what like the criminal risk score people like care most about, like sort of like the classical people designing. I
would say so. I don't think that's. I think that's what they say. I don't think that's actually what they care about fundamentally, because what they're doing is they're fitting a logistic regression, and they're using all the data, and that's a much stronger thing than calibration. That's really getting very close to this notion of multi-calibration, although they don't use that terminology, and it's really getting close to our intuitive notion of what it means to say someone's like true probability of risk, even though that's not fully defined. So it's a much stronger thing that they care about, even though they don't use those words. So typically they'll show something like this, but the point is just looking at something like this doesn't tell you very much. Knowing the process by which the scores were generated tells you a lot more. Okay, so now I want to switch. So that was kind of the brief overview of calibration. So now I want to switch to classification parity. And here, this is anything that can be computed from a confusion matrix, roughly. So think about false positive rates, false negative rates, precision, recall, all of these types of things. And I'm going to talk about false positive rates, but the argument extends to all of them. Just to refresh your memories, what is false positive rate? In this particular context, this means among people who would not have reoffended, what proportion were deemed high risk? And here it's just, you just have this binary classification at the end. So among people who are not reoffended, what proportion are deemed high risk? And you can compute this across different subgroups of the population. For example, ProPublica did this for black defendants and white defendants and determined that the false positive rate for black defendants was about twice as high and quite big, 30% versus 15% for white defendants. So a quite large gap in false positive rates across groups. Now, I'm going to argue that this doesn't mean exactly what it's commonly interpreted as meaning. And so you look at these numbers and you're like, oh, this feels like really bad, like something has gone wrong in the algorithm itself. I'm saying it's a more nuanced argument here about what's going on that I'll try to work through. And the issue is, at a very high level, what is the issue? The issue is that we typically think of error metrics as comparing different models on the same data set. And here what's happening is something different. We're looking at the same model on different data sets, different subgroups of that original data set, so effectively different data sets. And when we take this, we take an error metric and we compare the same model across different data sets, that's an apples to oranges comparison that is not at all the same as a typical apples to apples comparison of different models on the same data set. So it's a very kind of subtle difference, but that difference has enormous impact on the interpretation of these numbers. Okay. So let's just, again, mechanically see how these things are calculated. We have our two groups. Remember, any two groups will likely have different distributions of risk. That's not a statement about kind of the, like some sort of moral statement about whether one group is riskier than another. It's just saying that the covariate distribution is different across groups, and so we have different estimates of risk across these two groups. In here, we're going to take this kind of simple thresholding decision rule to say who is detained and who is released. And now let's just compute false positive rates for the blue group. How does this work? Again, it's among people who do not reoffend, what proportion were deemed high risk. These are the probabilities that they reoffend, so we can just go 1 minus this, add them up. That's not quite right, but some approximation of that will give us the denominator. And the numerator is among those people, how many are to the right of this line. So we do this, and we get 2 over 8. So we get 25% false positive rate. We do the exact same thing for the red group. So now this is a higher risk group on average, higher recidivism rate. So the proportion that do not reoffend is going to be smaller. And in this particular example, more of these people who do not reoffend are to the right of the line. So again, just mechanically, we have a higher false positive rate, about 40% false positive rate in this example. So again, just recapping, we have very big differences in false positive rate. Where's it coming from? From this very simple reason that the distribution of risk is different across these two groups. So even if we apply the same threshold, we will just get different false positive rates. Okay, so again, it's not because there was a different standard being applied to different groups. It's because different groups have different distributions of risk. So applying the exact same standard leads to different false positive rates. So this is what's happening. So this is just kind of a stylized example, but it's pretty close to what we think is happening in the real data. So here are estimates of recidivism for individuals in the ProPublica data. And we again see this heavier tail for black defendants. And again, we don't know exactly what the sort of true risk is for individuals, but these are estimates of that. And we see that the tail is heavier for black defendants than white defendants. And so that's in line with where these higher false positive rates are coming from for black defendants relative to white defendants. So now, kind of relating this to classical econ, this is what's called infra-marginal statistic. False positive rates are infra-marginal in that they average over the entire distribution. So to compute false positive rates, I have to know something about the entire distribution. But ideas of discrimination, particularly taste-based discrimination, are ideas about what's happening at the margin. So this idea that you apply a single standard to all individuals in the population, that's a margin, that's like talking about what's going on at the margin, but the summary statistics, things that you can typically compute from a confusion matrix are integrating over the entire distribution. And so that's where this mismatch is coming from. So this is like an idea of, this is one of the reasons why it's so difficult to estimate discrimination in human decisions, because we don't usually have the entire distribution of risk. And so it's hard to know if people are applying the same standard. And that's where a lot of our work is actually is pushing on, is understanding discrimination in human decisions, and where infra-marginality is the biggest concern. Okay. So now I'm going to kind of go back to this example and say why this is even weirder. So you might say, okay, well, false positive rates, maybe they mechanically came from this this difference in distributions of risk, but there still might be something kind of bad, like the group itself might be experiencing harm when you're thresholding using a single threshold to make these types of decisions. And I would say yes, that's possible. Like it's not to say that a single threshold is the only thing that one might want to do. You might want to have different thresholds for different groups because you think the equilibrium properties of that type of decision rule are good in some sense. But I'm also going to push back a little bit and say that it's not a priori obvious that just because false positive rates are different, then the group with the higher false positive rate is being harmed. So why is that? So a very simple example. So let's look at this red group. The red group is the one with the higher false positive rate, the 40% false positive rate. Now, what am I going to do? I'm just going to go out and arrest a bunch of college protesters. Just a bunch of low-risk people. I'm going to add into my population. And now what's going to happen when I do this? Well, all these people were identified as low risk by the algorithm correctly. No one's decision is going to change except for these people are going to be released. So they're going to be immediately arrested and then released. And so what's going to happen, these folks are mostly going to end up in the denominator over here. No one's going to end up in the numerator. None of them are to the right of that dashed line. And so my false positive rate just mechanically falls. Okay, so I've gone from this situation where one might say, well, false positive rates are high for this group, so this group is experiencing real harms, to this, where all of a sudden the false positive rate is equal, but the groups are not, the group arguably is worse off in this particular case. Just in the interest of time, I'll postpone this to the end of the questions. And so again, this isn't to say that that the only thing to do is to draw a threshold, and maybe something funny is happening, but without any extra information, you don't know if this is a good situation or a bad situation, because I can easily flip what you might naively say just by changing this distribution of risk. So without knowing something more about what this population is, it's very hard to interpret things like false positive rates. Okay, so again, all of these definitions that precision, recall, false positive rate, false negative rate, they all are inframarginal. They all have exactly the same statistical property of requiring the full distribution of risk to compute, even though at least some common notions of equity depend on what's going on only at the margin. And that's where this mismatch is coming from. So now, let me, just in the interest of time, let me skip to the end. I'm going to not talk about the anti-classification, but I'll show the reference to a paper at the end. And let me just talk a little bit about bias in the data, but this is an important thing to consider. So again, bias in the data, that's not like a totally well-defined idea of what this means. So I'm gonna give two interpretations of what bias in the data might mean, and then play out how what the consequences of these things are. So the first is bias labels. This is what I alluded to at the beginning, that Y doesn't perfectly measure what we care about. And the second is bias predictors, in that the features are differentially predictive. So I'll argue that this is a huge problem, and this is not as big a problem when you don't have bias labels. Okay, so that's what I'll try to argue. Okay, so let me give you an example. I think this is probably an example that many people know. St. George's Hospital in the UK developed this algorithm to sort medical school applicants. Trained, the label here was past admissions decisions. That's not a crazy label, I would say, in this setting. The problem is that past decisions were biased against men and women, and so the algorithm just codified this discrimination. And the issue again is one of mismatch. That the label, the true label, is something like how successful would this person be if they're admitted into the program. That's very hard. And so the proxy label is what did somebody decide in the past. Now, to the extent that the proxy label is not well aligned with the true label, you have this codifying of discrimination in your algorithm. So this is something we always have to contend with. In the criminal justice setting, what does this mean? This is something of like the difference between whether or not someone committed a crime, committed an assault, and whether or not they were arrested or convicted for that assault. Even conviction is clearly not the appropriate proxy, or not the close proxy to what is happening in reality. And so if you think of something like drug arrests, this is super problematic. And so we know from survey data, we have strong reason to believe that drug use is similar across groups, but because of heavier policing in high crime, high minority neighborhoods, we will arrest somebody and ultimately convict them for using drugs more often if they're a minority than if they're white. Other crimes, like violent crime, it seems less prone to this, but we don't really know. I mean, this is part of the difficulty here is we don't know what we don't know, and so we don't actually have those true labels at the end of the day, and so we're always making some inference. But the hope, at least, is if it's not street crime, it's less less susceptible to this observation bias that we have for crime. But it's very difficult to estimate these things. So that's a clear problem on the bias label side. On the bias predictor side, what does this mean? So I think one intuitive sense in which we might have biased predictors is that using this marijuana arrest example again, is that minority users are more likely to be arrested than white users. We have that fact. And so therefore, if I'm trying to make some prediction of, let's say, like violent crime based on the number of times you've been arrested, actually means less if you're a minority than if you're white. So if I know that I'm trying to predict violent crime, so there's no bias, let's just assume that there's no bias label problem here, but still, let's say every time you're arrested for marijuana, every time you have a marijuana arrest, that might increase my estimation of you by like 1% on average, that you will commit this violent crime if released. But the problem is that number doesn't really mean the same thing across different groups, because you're more likely to be arrested if you're black than if you're white. Okay, so statistically, this is a very simple thing to fix. If you believe the labels are unbiased, you just fit two different models. And you say, okay, well, maybe every marijuana arrest will add half a percentage point if you're black, and it'll add 2 percentage points, or 1 percentage point, 1.5 percentage points if you're white, something like this. Okay, so this is statistically a very kind of easy thing to do. It's contrary to this idea of anti-classification. Anti-classification, I didn't really go over it, but it just means this idea that you don't use protected characteristics explicitly. And here we are using those protected characteristics explicitly to correct for the fact that there's different amounts of information in the labels themselves, in the features themselves. So this is, I think, a nice kind of description of this by Sandy Mason in her Bias In, Bias Out paper. In New Orleans, when I worked there as a public defender, the significance of arrests varied by race. If a black man had 3 arrests in his past, it suggested only that he had been living in New Orleans. Black men are arrested all the time for trivial things. If a white man had 3 past arrests, on the other hand, it suggested that he was really bad news. So exactly the same thing, that we have different information, and the same predictor might mean different things in different groups. We actually haven't found empirical evidence for this, although we're not looking in New Orleans. But conditional on all the other features, we don't see differential predictive power in race, although we see huge differences for gender. So it's just like sort of interesting empirical observation that once you conditional on lots of stuff, the impact of race seems to be small in the examples that we're looking at, although I do suspect there are examples where that's not the case. In gender, it's quite huge. Okay, so now just wrapping up in the last minutes, I think there are all these formal mathematical definitions of fairness, but the main thesis of this talk is that many of these definitions cannot accommodate common understandings of equality, particularly something like a single threshold rule applied to our best estimates of risk. And that's not to say that this is the only way to think about equality. I don't think that is the only way to think about equality. But again, I do think of this as a litmus test. And if these notions like false positive rates are really being used widely and fail to capture what practitioners are doing, and also what our legal system, I would say, has said is okay, we should at least think about what the implications of those formal definitions are. And the last point is that algorithms are not policy. And so algorithms, can I just wrap this up, and then this is the last slide. So the statistical algorithms, what is the role of them? They're good at synthesizing information. And so the algorithms might say, well, give me a bunch of features. I'm going to give some estimate of some outcome happening. They don't tell us what to do. And so in the pretrial setting, one thing that many are advocating for, including myself, is to limit money bail entirely. This is where California is heading. And we might say, or go to these non-custodial interventions. And so even if someone is high risk or high flight risk, we know statistically that are high risk of flight, we might not just detain them. We might say, well, let's get you childcare, let's get you transportation, and let's deal with that underlying issue of lowering someone's risk. And so the algorithm can correctly tell us that someone is high risk of some certain adverse impact. It's not telling us what to do. And I think a lot of the issues that people have with equity in the criminal justice system is not the actual estimation of risk itself, but what we're doing with that thing at the end. And so saying that because I've estimated you to be high risk, I'm going to impose all these kind of harsh conditions on you, in many cases I would say is not appropriate. And so we can, but it is accurately telling us ways that we can intervene. For example, enrolling someone in some sort of transportation program or something. So that's actually one of the directions that we're moving in now, is developing interventions to lower someone's risk. If you're interested in more of this, check out our papers. This pretty much is kind of the paper version of the talk, and this other paper came a little bit earlier, and it's going into some of the more technical details of this. And if you're interested in learning more about the interventions that we're starting to roll out, please check out our webpage. Thanks.
Time for 1 or 2 questions while Charlie sets up?
Just a comment to go back to that slide. I mean, the title of the slide, if you go back to it, which says math does not equal equity or something,
Yeah.
math does not imply, I mean, that's not consistent with the content of your talk or with what you were saying, I think. And there are particular notions, mathematical notions of fairness, which do not imply equity. That doesn't mean that math can't be helpful. And on the contrary, I think math is very helpful for reasoning, for you actually showing why this particular notion doesn't imply fairness.
I agree. So the title of the slide was math is not equal to equity, not that it's not sort of something that's useful. And so I do think it's useful, but what I see, and again, this is, maybe this is a controversial statement, but I do think it's true that a lot of papers will simply posit a mathematical definition and equate it with justice or fairness. And this maybe is just like loose language, but I think it's important that whenever we write down any formalization of an idea, that we understand this is a particular formalization, that it's not the kind of broader sense in which we care about these issues. And so that's where I'm coming from. So I do certainly think, of course, I'm trained as a mathematician. I kind of am professionally required to believe that this stuff is useful in a sense. But I also think it's important to not kind of naively equate them.
Maybe in the interest of time, we can take the remaining questions over lunch and drinks.